Since the dawn of humanity, we have always been driven by a desire to explore space and distant planets. From the historic Apollo missions that first took us to the moon, to the advanced Mars rovers uncovering secrets of the Red Planet. Each step into space has ignited our imagination and expanded our understanding of the cosmos. However, there's a significant hurdle that stands in the way of this ambition: the high costs of space programs. These substantial expenses result in limited accessibility, preventing many smaller countries, organizations, and educational institutions from participating in space exploration. The barriers are steep, and the playing field is far from level. This is where CubeRover comes into play. Inspired by the practical modular approach used for CubeSat, this concept is applied to rovers to create a standardized architecture for small, modular planetary rovers. These rovers feature compatible parts, systems, and instruments, enabling each mission to be easily customized to meet its specific objectives. CubeRover is being developed by Astrobotic Technology in partnership with Carnegie Mellon University. Astrobotic Technology, commonly known as Astrobotic, is an American private company dedicated to developing space robotic technology for lunar and planetary missions. To better understand this concept, let's break it down into several key components: structure, thermal control, mobility, avionics, which stands for aviation and electronics, communication, power, and perception and teleoperation. CubeRovers come in different sizes, each tailored for specific mission requirements. Here are the primary models and their specifications. The 2U CubeRover with a rover mass of 5 kg supports a payload mass of 2 kg, a payload power of 1 watt, and a payload volume of 20 cm by 10 cm by 10 cm. This specification was used for the first flight-worthy CubeRover, which was launched on the 8th of January 2024 along with Peregrine Mission 1. The rover, named Iris, would have been the first American student-developed, smallest and lightest rover to land on the moon. Unfortunately, surface operations were halted due to a propellant leak that developed shortly after the Peregrine lander separated from the Vulcan rocket in lunar injection orbit. This leak prevented the lander from completing its mission. After 6 days in orbit, the spacecraft was redirected into Earth's atmosphere, where it burned up over the Pacific Ocean on 18th of January 2024. Back to the different sizes. The 4U CubeRover, with a rover mass of 8 kg, supports a larger payload mass of 4 kg, a payload power of 2 watts, and a payload volume of 20 cm by 20 cm by 10 cm. The 6U CubeRover has a rover mass of 10 kg, a payload mass of 6 kg, a payload power of 3 watts, and a payload volume of 30 cm by 20 cm by 10 cm. In addition to these, there are larger models, including 12U, 24U, and even bigger configurations, each designed to accommodate more complex and demanding missions. So, the thermal control system regulates and manages thermal interfaces for the payload in the CubeRover subsystems, ensuring optimal performance and protecting against extreme temperature in space. The system is crucial for maintaining the operational integrity and longevity of the rover's components. So the key components of the thermal control are the radiator. So the top panel of the CubeRover functions as a thermal heatsink for all components, excluding the solar panels. All thermally regulated components are grounded to the bottom of the space-facing radiator on the rover. Multi-layer insulation. The exterior of the CubeRover chassis is wrapped in a multi-layered insulation blanket. This significantly reduces the heat loss to the harsh environment of the deep space and the lunar regolith, effectively maintaining the internal temperature of the rover. Electric heaters are used to maintain payload temperature during the mission. For payloads mounted externally on the CubeRover, thermal management is achieved using electric heaters in conjunction with a conformal MLI implementation, ensuring precise temperature control. Wheel spokes. A concern for any lunar rover is the amount of heat loss through the wheel rims, both via conduction to the lunar surface and via radiation to space. CubeRover's unique wheel structure uses long, thin, non-metallic wheel spokes to isolate and maintain the payload's temperature, even when the wheel rims reach extremely cold temperatures. So, for mobility, CubeRover uses a fixed-axis four-wheel independent drive system with skid steering. Each wheel is powered by an actuator system that includes a motor, planetary gearhead, encoder, wire harnessing, thermal strapping, and a wheel mount. The wheel rims of CubeRover are crafted to provide maximum traction, enabling it to navigate uneven surfaces and loose regolith. Rigorous mobility tests, including drawbar, pull, and slope climb tests, are conducted at Astrobotic Lunar Regolith Lab.
You might want to be ready, Armor. This is the stop. Yeah, and whenever you want to stop, just hit that whole wheel. Stop when the left wheel hits that highest point there.
These tests use GRC-1 Lunar Regolith Simulant and a reduced mass rover to accurately replicate soil-wheel interactions in a lunar environment. Here are the key results from the 2U CubeRover mobility tests. The maximum demonstrated slope climb is 25 degrees, showcasing its ability to handle steep inclines. The maximum demonstrated step-up height is 10 centimeters. In terms of speed, the standard drive speed is 4 centimeters per second, while the maximum drive speed can reach up to 10 centimeters per second. And the CubeRover boasts a maximum ground clearance of 7 centimeters on a hard surface, ensuring it can traverse rough terrain. Avionics. CubeRover's avionics system is designed with an integrated avionics unit that handles power distribution, data processing, controls, and communications. This compact setup minimizes potential failure points and reduces weight. The integrated avionics unit mounted directly to the radiator to optimize heat transfer away from sensitive circuits. The IAU has data storage of up to 4 GB and consists of a carrier board plus processor board. The primary processor manages incoming commands from the ground, triggering the camera system, commanding motor controllers, and handles system data storage and retrieval, as well as payload commands. To ensure safe and reliable operations, a separate processor serves as a watchdog monitor, capable of resetting or power cycling the radio and main processor in case of errors. This monitor also handles temperature sensors, heaters, and a solar battery charging circuit. The primary flight software on the microprocessor uses a lightweight real-time operating system and utilizes Flight Heritage software framework developed by NASA. This software interprets commands from the ground through the radio and transitions between different modes such as roving, imaging, standby, general operations, and safe mode. Communications. CubeRover leverages Astrobotic's lander communications network to receive commands and send telemetry data. The Astrobotic Mission Control Center communicates with the lander through ground station dishes using X-band frequencies for both uplink and downlink. The lander then communicates with CubeRover via a serial wired connection during transit and a 2.4 GHz Wi-Fi connection after CubeRover is deployed to the lunar surface. For missions exceeding 200 meters from the lander or lasting longer than one lunar day, A long-range S-band communication system can be replaced with the Wi-Fi system. This enables CubeRover to communicate with Earth via a lunar orbital relay satellite, eliminating the communications-dependent limit on its range from the lander. Power. CubeRover is rechargeable, allowing it to generate continuous power during mission operations. During transit to the Moon, CubeRover connects to the lander via an electric connector, receiving power directly from the lander. Once on the lunar surface, the rover deploys its solar panels equipped with Flight Heritage solar cells. These panels generate continuous power as CubeRover roves across the Moon. There are two standard solar panel configurations, one optimized for equatorial regions and another for polar regions. This flexibility ensures CubeRover can operate in any lunar environment. CubeRover's avionics include DC to DC converters and circuits that manage power distribution to various subsystems and customer payloads. A dedicated battery monitor circuit oversees the lithium iron phosphate batteries. The advantage of an LFP battery is its thermal and chemical stability, which improves safety. Additionally, LFP chemistry offers a considerably longer cycle life than other lithium-ion chemistries. Perception and teleoperation. CubeRover's cameras and teleoperation system allow payload customer to monitor and drive the rover throughout the mission. It is capable of capturing and transmitting images of varying sizes and compressions. Two monocular 1.3 megapixel cameras are used for navigation, with additional customer camera arrangements also possible. The ground control subsystem is designed to achieve the highest possible speed made good, within the constraints of safety. Speed made good measures the distance the rover travels over a given time. It is directly affected by factors such as move distance, move planning time, operational time, image size, effective bandwidth, and transmission delays. Payload accommodations. To support a wide range of mission objectives, CubeRover offers flexible payload accommodations, including non-standard placements such as top-mounted, bottom-mounted, front-mounted, and back-mounted options. These additional placements may incur extra costs, but can be used as, for example, to collect lunar surface data and images, perform experiments and validate new technology in the lunar environment, conduct resource prospecting and lunar material collection, deploy antennas, place cables, and establish other infrastructure elements on the lunar surface. CubeRover key benefits. CubeRover offers a range of advantages designed to meet diverse mission requirements effectively. One of the primary features is scalability, with flexible sizes such as 2U, 4U, 6U, up to 12 and 24U, and even larger ones. Mission planners can select the appropriate rover size that aligns with their specific needs and payload requirements. Another benefit is customizability. CubeRover can be adapted to meet specific mission objectives, including surviving the lunar night. This level of customization ensures that each mission can be tailored for success. The modular nature of CubeRover allows it to carry various types of payloads, from scientific instruments to communication devices. This versatility makes CubeRover suitable for a wide range of missions, including scientific research, resource exploration, and technology demonstration. Affordability is also a key advantage. By using standardized modules, new CubeRovers don't need to be designed and built from scratch for each mission. This reuse of components substantially reduces development costs. Additionally, CubeRover's lightweight design results in significantly lower costs for payload customers compared to traditional rovers. This cost-effectiveness makes CubeRover accessible to universities and smaller companies, enabling broader participation in space exploration. Lastly, CubeRover's test that reliability ensures its suitability for various mission requirements. Their modular, scalable, and customizable design means that most of the parts have already been tested and proven, offering a dependable solution for diverse mission needs. So, CubeRovers present an opportunity for universities, smaller countries, and companies to participate in space exploration, thereby advancing scientific research by lowering the barriers to entry. These small rovers are poised to enhance space exploration, offering numerous benefits compared to conventional rovers. Looking towards the future, CubeRovers are not only valuable for lunar missions, but also hold potential for Mars missions. Their compact size and capability to operate in parallel make them particularly efficient at exploring larger areas. Deployed from multiple landers, CubeRovers can act as scouts, identifying safe paths through hazardous regions and paving the way for larger rovers on follow-on missions. This capability could be crucial in our efforts to explore and eventually colonize Mars.